Censorship.
Okay, so I'd like to start by thanking the organisers for inviting me to this fantastic conference. So I'm going to be talking about work carried out with Gary Horowitz and my supervisor, George Santos. And when this work began, it wasn't expected that it would have anything to do with the title of this conference. So we've been looking at possible counterexamples to the cosmic censorship conjecture in anti-de Sitter spacetimes. Now, cosmic censorship is a conjecture in classical GR, so what's that got to do with the Swampland? But it was pointed out to us by Kumran that these counterexamples to cosmic censorship that we've been studying, that they might go away if the conditions of the weak gravity conjecture are assumed to hold. So in other words, we might only be able to violate cosmic censorship if we work with a theory that lies in the Swampland. And if that's true, then it points to an intriguing connection between these two conjectures, which is what this talk will be about. So in the first half of the talk, I'm going to present numerical evidence that the weak cosmic censorship conjecture is violated for the Einstein-Maxwell equations in 3+1 ADS. And I'll explain exactly what we mean by that statement in a moment. And then in the second half of the talk, I'll argue that these counterexamples can be avoided if you include a sufficiently charged scalar field in the action, as the weak gravity conjecture tells you to do. So we have an electromagnetic interaction. The weak gravity conjecture says we need charged particles. Maybe not necessarily a scalar, but we'll only deal with scalars in this talk. And then if there's time at the end, I'll just very briefly talk about the results of some very recent and ongoing work, which kind of undermines the main message of the talk a little bit, which is why I'll only mention it briefly at the end. So we've been looking at similar potential counterexamples to cosmic censorship, which occur for the vacuum Einstein equations. And that's important because it's much harder to see how the weak gravity conjecture could play a role in these examples, although I believe there have been some ideas about how you could make something work. Okay, so I'll start by reviewing cosmic censorship. So we all know that GR predicts the formation of curvature singularities. That's a classic example being gravitational collapse. And the interpretation of these singularities is that they signal the breakdown of the theory. So we know that GR is not a complete theory, so we shouldn't be surprised that it predicts regions where it breaks down and where new physics takes over, presumably a quantum theory of gravity. But what is perhaps surprising is that in typical examples, these singularities are contained within black holes. And that means whatever goes on there, whatever new physics takes over, it has no observable consequences for anyone outside the black hole. And a very rough statement of cosmic censorship is that this always happens. So the universe is conspiring to hide this new physics from us. So this obviously has very important implications. So on the one hand, you could view it as a blessing. It's the reason that you don't normally have to worry about quantum gravity in astrophysics. So if you want to model the collision of two black holes, you can safely do that on a computer without worrying about the fact that you don't understand what goes on at the singularity. But you can also view it as a curse. So it means that it's difficult to do quantum gravity experiments even in principle, because one good place to test quantum gravity would be in curvature singularities. But cosmic censorship means that if you want to get information about what goes on there, you have to jump into the black hole, and then it's very difficult to tell people your results. Okay, so that was the intuition behind cosmic censorship. I should now define it more precisely. So in asymptotically flat spacetimes, there's a mathematically precise definition of the weak cosmic censorship conjecture, which talks about the completeness of future null infinity. And you could imagine generalizing that definition to ADS, and talk about the completeness of the ADS boundary. And if you do that, then it turns out the examples I'm going to show you, it turns out actually don't violate cosmic censorship according to that strict definition. But we still believe that they violate the spirit of cosmic censorship in the following sense. So when we say cosmic censorship is violated, what we mean is that we have an open set of smooth, geodesically complete initial data, such that for all solutions constructed from these data, some curvature invariant is unbounded in a region visible to observers at infinity, or at the ADS boundary, I should say. So notice we don't require that the curvature becomes infinite anywhere, that it actually blows up. But what this definition means is that whatever the curvature scale is where new physics kicks in, a distant observer will eventually be able to see that if they wait long enough. And that's the reason we describe this as cosmic censorship violation. And the open set condition is there just because it's trivially easy to violate cosmic censorship if you can fine-tune your initial conditions, so we need to rule those examples out. Okay, so with that definition, is cosmic censorship ever violated? And the answer is yes. So the classic example is when you go to higher dimensions, 4+1 dimensions or higher, you have these black string or black ring solutions, and they suffer from the Gregory-Laflamme instability, and the endpoint of that instability is believed to be a naked singularity. But cosmic censorship is still believed to hold in 3+1 dimensional asymptotically flat spacetimes. So what about ADS? So there it's more complicated. So anti-de Sitter spacetimes suffer from the superradiant instability, and it's been suggested that that might violate cosmic censorship. But I won't be discussing that in this talk. What I'll be talking about is the following. So we have numerical evidence that cosmic censorship is violated when you have a gauge field without a corresponding charge scalar, or a U1 gauge field. So that's the examples I'll describe now. So the setup is the following. We take the following action with, so it has gravity, it has U1 gauge interaction, and it has negative cosmological constant. We need to provide initial conditions. So we're going to just start in the vacuum of ADS, so there'll be no gauge field. We can write the metric in the following form. So we work in the Poincare patch. The z coordinate here is the bulk radial coordinate. So z equals 0 is the ADS boundary. And when we talk about distant observers, we mean observers at the ADS boundary. Z equals infinity is the Poincare horizon. So that's the surface which separates points which are in causal contact with infinity, or with the boundary, from points which are not in causal contact with the boundary. And the remaining coordinates parameterize the boundary directions. And we're going to assume a symmetry in the boundary direction, a rotational symmetry in the boundary directions. So that's a symmetry in this phi coordinate. You might worry that that means our examples are fine-tuned and not generic. But we have arguments that the story I'm going to tell you carries over even if you weaken the symmetry assumptions, even though we haven't done the numerics for that case. Now, because this is ADS, we have a time-like boundary, so we also need to provide boundary conditions for each of our fields. So for the metric, we just impose a flat metric at the boundary. But for the gauge field, we impose the following non-trivial boundary condition. So this corresponds to introducing a localized lump of electric field at the boundary, which decays as you go off to r equals infinity. And the amplitude of this lump we can choose to vary in time. So it has to start at 0 to be consistent with our initial conditions, but then we can increase it in time, and that will drive our system away from the vacuum and, we hope, force the creation of a naked singularity. So why do we expect that to happen? So these are the key points. So in this paper, these authors looked at stationary solutions of the kind I've just shown you. So with a boundary profile that was independent of time. And what they found was that there were no stationary solutions above a critical amplitude A max, where A max depends on the rate of decay of the boundary profile. And what's more, in the stationary solutions they did find, as the amplitude approaches A max, the curvature diverges on the horizon. So this raises the question, what happens if you, in the time-dependent problem that I've described, if you increase A with time from an initial value of 0 to a value A0, which is larger than A max, and then you wait for the system to settle down? So this is a puzzle because it seems like there's no stationary solutions that the system can settle down to. Now, that's not quite true. So there are stationary solutions with arbitrarily large amplitude, but they don't have a connected horizon. So they involve having small hovering black holes which hover just above the Poincare horizon. And the gravitational interaction tries to pull them into the Poincare horizon, but the electromagnetic interaction, because these hovering black holes are charged, tries to pull them out to the boundary. And you get a stationary solution with a hovering black hole in stable equilibrium. And these solutions exist for arbitrarily large amplitudes. But the important point is that we, at the moment, have no charged matter. And that means that it should be impossible to form these hovering black holes dynamically. So they can't be the endpoint for the evolution if we do this experiment. So what does happen? Well, in this paper, these authors conjectured that the result would be the formation of a naked singularity. And one way of motivating that is to imagine what happens if you vary the amplitude very slowly, because then you might expect it to approximately track the stationary solutions that they'd already found. And in that case, the curvature diverges on the horizon, so that's a point that's visible to the boundary as A approaches A max. Okay, so that's the plan. So we did that. We solved the full time-dependent problem numerically, and here's our results. So this is a plot of you can think of this as a plot of essentially the space-time curvature on the horizon as a function of time for various choices of the final amplitude A0. And the smaller two amplitudes here are below A max, and the three larger amplitudes are above A max. Now remember, we increase the amplitude from 0 initially to A0, but that all happens within about 1 unit of time. So after 1 unit of time, you can think of the boundary conditions as essentially being held fixed at A0. And I said this was a plot of the space-time curvature. It's actually a plot of f squared. But f squared is a scalar quantity, so it should be telling us something physical. It's simpler to compute, which is why we plotted f squared. And we have an argument that if f squared is diverging in our solutions, then the Kretschmann should be diverging as well. So what do we find? So for the two smaller amplitude cases, here's where we expect the system to be able to settle down to a stationary solution, because these were the stationary solutions found in the original paper. And our results are consistent with that. So these dotted lines represent the value of f squared in the stationary solution, and our results are consistent with settling down to that value. What about the three larger amplitudes? Well, on this plot, the behavior looks qualitatively similar to these two cases, but we don't expect them to be settling down to a stationary solution of the kind that was found before, because none seemed to exist when they were studied. So the claim is that in these cases, f squared never stops growing, that it will continue to grow without bound. How can we check that? Well, so one thing we can do is look at the time derivative of f squared. So if the time derivative is decaying faster than 1 over v, then that means f squared is converging to something. If it's decaying slower than 1 over v, then that suggests f squared is growing without bound. So this is a plot of the time derivative of f squared multiplied by v. And you can see in the two smaller cases that's consistent with decay. But in the two larger cases, this quantity is growing. So that's indicating that f squared is growing without bound. The middle case has not started growing yet. Maybe it will if we could evolve it further. We can understand this, though, from the fact that this amplitude was very close to A max itself. So this is kind of an intermediate case. Perhaps the growth here is almost logarithmic. Okay. One final worry you might have is that these plots are all on the apparent horizon, which generically lies inside the event horizon. But we've looked at the behavior of null geodesics in these spacetimes and checked that this region is really visible to observers on the boundary. Okay, so to sum up the first half of the talk, I've shown you examples where if a distant observer waits for long enough, they should be able to see arbitrarily large curvatures. And for that reason, we say that cosmic censorship is violated for the Einstein-Maxwell equations in ADS. So what's that got to do with the weak gravity conjecture? So I won't review the weak gravity conjecture, mainly because I'm sure everyone here understands it a lot better than I do. But the rough idea, as has been said in previous talks, is that any consistent theory of quantum gravity with a gauge interaction should have a particle which is charged under that interaction, and the charge should obey this inequality. We're in ADS, and we have to ask whether that inequality needs to be modified. So one of the motivations for the weak gravity conjecture is that extremal black holes should be quantum mechanically unstable to pair production. In ADS, this instability is present at the classical level. It gives you the charged superradiant instability. And if we require that arbitrarily small extremal black holes are unstable, we obtain this bound. So here the charge is bounded by some quantity which depends on both the mass but also the ADS length scale. Okay, so here's the big question. It's like the question behind the whole talk. If we take the weak gravity conjecture seriously and we include a scalar field which obeys this inequality in our action, does our counterexample to cosmic censorship still work? And there's an immediate reason to suspect that it now might well not work. So if you remember, a crucial ingredient in our original motivation for why we expected to violate cosmic censorship was that there was no charged matter. And we needed that because we had to rule out the possibility that we might form these hovering black hole solutions, which existed for arbitrarily large amplitude and would give us an alternative endpoint for the evolution that would not involve a naked singularity. So that's the motivation for asking this question. Now, ideally, to check this, we'd repeat the time-dependent calculation again with a charged scalar included, and we'd check to see if these hovering black holes form. But that's quite hard. There's something simpler we can do, which just involves looking at the stationary solutions. So here's the idea. So we can ask whether the stationary solutions we had before are now unstable to forming scalar hair, now that a scalar field is included. Because if they are, and if these hairy solutions persist for arbitrarily large amplitudes, then these could provide yet another possible endpoint for our evolution, which would not involve the formation of a naked singularity, which would protect cosmic censorship. And the fact we check the stability means that these are the endpoints that we would expect to see if we repeat the experiment. So what's the answer to these questions? So the answer is yes, and the required charge appears to agree precisely with the weak gravity bound. So I'll show you how we got to this conclusion now. So the idea is we take the stationary solutions we had before, we solve the scalar field equation on these backgrounds fixed, and we look for zero modes to detect when scalar hair can form. And then we compute quasi-normal modes to check their stability. And if this all works, then there's a good chance cosmic censorship will be preserved. So here's our results from doing this kind of procedure. So this is a plot of the minimum charge that you need in order for scalar hair to be able to form on the stationary solutions. And this is as a function of the amplitude of the boundary profile. And we've plotted this for various choices of the decay rate of the boundary profile. That's what this n means. The charge here has been normalized by the weak gravity bound. So the dotted line at 1 here represents the weak gravity bound. And each of these plots terminates at A max, or the associated A max for that profile. And what we find is that in every case, just before we reach A max, this curve just dips below the dotted line. And that's telling you that just before your stationary solutions become singular, well, if it tells you if the weak gravity bound is obeyed, then just before the stationary solutions become singular, they will become unstable to forming scalar hair. So this is a good sign. There's a remaining thing we need to check. We need to look at the full nonlinear solutions with scalar hair and make sure that they don't also become singular above a certain amplitude. Because if they do, then all we've done is just shift A max higher, and the same argument we had before will just go through again. Okay, so we've checked that as well. So here, for the n equals 8 case, we've extended the plot from before with this orange line. And what this orange curve represents is the charge at which the hairy solutions become singular. So the idea is you pick a solution with scalar hair, which has some charge for the scalar field, and then you try to reduce the charge as much as you can until the curvature blows up. And where that happens, you put a dot on this curve, and that's how this curve is produced. And what you find is that as the amplitude goes to infinity, this curve appears to approach the weak gravity bound. And what that's telling you is that not only does the weak gravity bound seem to be sufficient to protect cosmic censorship, because if it's obeyed, then the hairy solutions are non-singular for arbitrarily large amplitudes. But it also means the weak gravity bound seems to be necessary to protect cosmic censorship, because if you had a charge which was slightly below this bound, then although you might be able to form solutions with hair, when the amplitude becomes very large, they will still break down, and the original argument we had for cosmic censorship violation could still be applied. Now, there's a big caveat here, which is that we haven't said anything about the hovering black holes. So these, as I said, can provide an alternative way of an alternative endpoint for your evolution that avoids cosmic censorship violation. So this weakens the claim that the weak gravity conjecture is necessary. Really, we need to check these kinds of solutions as well, but not the claim that it's sufficient. Okay, so to sum up the main points of the talk, it's important to know whether distant observers have to worry about curvature singularities or not. We've numerically constructed solutions in ADS to the Einstein-Maxwell equations and found evidence that a naked singularity can form. And finally, looking at stationary solutions with a charged scalar suggests that the weak gravity conjecture is sufficient and may be necessary to avoid these counterexamples to cosmic censorship. And that suggests an interesting connection between the conjectures. Okay, there's a but. So I said at the start I'd talk about some recent results which undermine this picture a little bit. So recently we've been looking at similar potential counterexamples to cosmic censorship which occur for the vacuum Einstein equations. So no gauge field. The setup is very similar, but instead of a gauge field, we impose a non-trivial boundary condition on the metric of the following form. So these cross terms here take the role of the gauge field from before. Now, instead of imposing an electric field on the boundary, we're imposing a differential rotation, if you like. And again, what you find if you look at the stationary solutions of this kind, so with no time dependence in the A's, you find that things go wrong when AT becomes big. And actually, it's easier to understand why that is in this case than it was in the electromagnetic case. So if you just imagine the case where there's no R dependence, you just have a planar black hole. If you were to hold AT fixed on the horizon and increase it to 1 on the boundary, then the angular momentum would blow up. Something would go very wrong. Now, that particular thought experiment is not something you can do dynamically because that's just increasing AT everywhere on the boundary is just a pure gauge transformation. So you wouldn't be able to hold it fixed on the horizon. But you can imagine that that gives you an intuition for what happens when the gradients in R are small. A hydrodynamic approximation, if you like. And so in that case, you might expect that if the difference between AT on the horizon and the boundary ever gets above 1, then something bad is going to happen. And you can force that to happen by making AT vary by a sufficiently large amount on the boundary. So what you're effectively doing is using the boundary conditions to overspin the black hole, something that people have tried to do to violate cosmic censorship in flat space. But here in ADS, we have boundary conditions to help us force that to happen. Now, from the description I've just given you, it might be clear that there's some important differences between this example and the electromagnetic example. So here's just a few of those. So here the counterexamples exist at finite temperature, whereas for the electromagnetic case, we were always at 0 temperature. The positivity of energy is less clear in this case. So all the ways of violating cosmic censorship here appear to involve introducing an ergo region on the boundary metric. And it's less clear that you have a positivity of energy theorem in that case. And if you don't, then maybe these new counterexamples to cosmic censorship are kind of trivial. And finally, in these examples, the boundary stress tensor blows up. So the angular momentum density diverges, whereas before all the boundary currents were under control in the electromagnetic case. So we're still working hard to try and understand these differences and understand the status of the weak gravity cosmic censorship connection in light of these new results. So yeah, thank you for your attention.
Maybe you have already studied this, but I don't know if you have. So in this context, in the last context that you just raised, have you studied the case of adding spinning objects with correct mass related to the extremal black hole? See if that resolves it or not? No,
so we haven't done that. So it's Would that be like a fermion, you mean, or?
Well, you can do fermion or whatever, but the idea is that is the issue related to black holes is basically the question. In the weak gravity conjecture, that the extremal bound was related to the black hole bounds. There's no sharp formulation of that same condition in the context of spinning, but it's natural to expect there's a similar condition. We know there are spinning black holes and they're encountered by particles in some form. So adding particles which are close to extremality, would it resolve this problem? That's the question.
So adding particles with spin?
Sorry?
Adding particles with spin?
Yeah.
So
with the mass related to spin exactly according to the, with the mass less, well, let me see, in the direction of the mass that you want, mass less than or equal to whatever that.
Yeah, so I know it's difficult to include fermions and do numerical evolution, classical evolution with fermions.
Difficult in terms of doing it, you mean? In other words, it would be semi-classical in that context.
I was under the impression that there were more fundamental difficulties doing semi-classical evolution with.
So going back to the original thing that you guys showed, my original suggestion was not the version you actually checked. My original suggestion was to do with fermions. But that was difficult because you had to do particle creation. And so you guys beautifully translate that question to a scalar version of that, which is very clever. So you could presumably have this formulation in the second one is the same way, whether it's fermion or boson. I don't think that should be the relevant question. The question is, realize it with some bosonic field with spin or something. That should not be the issue.
Bosonic field with spin.
Sorry?
A bosonic field with spin. So like a
massive field. Massive field.
Yeah, I don't think we've considered that.
I think that would be very natural, very much parallel with the other one.
Okay, thanks.
So, I mean, I have this question that you said that you can see this naked singularity, but it's an infinite amount of time. So then you don't really see it, do you? Because you don't really have infinite amount of time. So why would you say that this kind of shows that there exists such kind of singularities? Is there something more to it, or is that kind of just it?
Yeah, so it's so it comes down to how you define cosmic censorship. And if you define cosmic censorship to mean that you need a curvature singularity which is visible at the boundary, then I guess that we haven't violated cosmic censorship. But if you think about the sort of motivation for why we care about cosmic censorship is because it hides these regions of high curvature from us. And what we're saying is that whatever the curvature scale is, when new interesting physics kicks in, we've got examples where that will be visible to distant observers. I mean, infinite curvatures don't really exist anyway, so I guess in practice, what's the difference between being able to form arbitrarily large curvatures and being able to see infinite curvatures? I don't know if that's a good answer or not.
Thanks.
So a couple of times you said that you had to introduce matter in order to produce these black holes. That I'm not sure I understand. Why can't you have a black hole by just a geometric field, for example, a collision between waves in a geometric field?
I think it's to do with, so there'd be nowhere to get the charge. These are charged black holes.
Oh, okay.
Yeah, sorry, I should emphasize that. So we need charged matter to be able to form the charged black holes. I don't think you should be able to form them just with Einstein-Maxwell.
All right. There are no more questions. Let's thank Toby and all the rest of the speakers.